Okay, we are on example 10.10. Well, quick check 10.10 rather. Okay, so this is showing you a potential energy versus displacement. Okay, so this is saying if it has 1 joule of kinetic energy at 1 meter, what, oh, sorry, I'm at the wrong one. Here we go. When potential energy right here versus displacement. So it's saying at 1 meter right here, it has 1 joule of kinetic energy. Well, this is just showing you potential energy. So that's showing you right here is 3 joules of potential energy. And it's saying from 1 meter to 2 meters right here, what's happening? So it's going from potential all the way down to 0. So what do you think that means then? If it's going all the way from this pretty high potential energy down, then that means that you are going from potential to kinetic. And if you're going from potential to kinetic, then that means that you're speeding up. Okay? Now this one it's the same exact graph. It's just saying a particle with the potential energy shown is moving to the right. It has 1 joule of kinetic energy. So same thing. Wants to know what is the particle's turning point. Okay, so if this right here is 3 joules of potential energy, and this is at 1 meter, and at 1 meter it has 1 joule of kinetic energy, then that means that the total energy is what? 4 joules. So at what point, what x position, does it get to the total potential? Because here's the thing, if it's the turning point, meaning that it's going to get all the way to its highest point and then it's going to turn back or fall back or whatever you want to say. So if you look over here at 4, you make a little dot there, that's at 6 meters. Okay, and that's its turning point. And then it goes on, the same slide again, it just wants to know at what, says the particle with this potential energy could be in stable equilibrium at what position? So it's stable when it's at its lowest point, so that would be at 2 meters. Okay? Alright, so those are some quick checks right off there. Alright, this is showing you conservative forces. So this figure shows a particle that can move from A to B along either path while a force is exerted on it. And if there's a potential energy that's associated with the force, then that is a conservative force. Okay? So the work that's done by the force as the particle moves from A to B is independent of the path. And so this is just showing you if it goes from initial to final position with a conservative force, okay, or conservative force, then you end up with this negative conservative work, okay? This is showing you kind of like the opposite. So a non-conservative force is if an object slides up and down a slope with friction. Okay, so if friction is involved, then it returns to the same position with less kinetic energy. And so just think about, like, for instance, and you guys haven't done this one yet, but you know, if you are like on a skateboard, okay, and you are going and there's no friction on here at all, no friction, okay, then that skater can just like go up and down this slope on and on and on, okay? But if there is friction involved, that skater is going to go down this curve and then they're going to go back, but they're not going to get to that position that they were, okay? So force with which we cannot define a potential energy is called a non-conservative force. And so friction and drag, which transform mechanical energy into thermal energy, are non-conservative forces. Okay, so there's no friction potential energy. And then it's saying that also like forces like tension and thrust are non-conservative. Just meaning that they're going to not, they're going to mess with that conservation of energy equation. You're going to lose some energy as heat or things like that. Okay, so this figure shows a system of 3 objects that interact, and they're all, it's showing that they have external forces from the environment that's affecting it. So non-conservative forces doing work. So if you say that, it says now let's make a further distinction by dividing the non-conservative forces into dissipative forces and external forces. So dissipative forces are going to start making it to where it doesn't move, okay, like friction and drag. And so then it gives you this energy principle again that is showing you that if you have the change of kinetic energy plus the change of potential plus the change of thermal energy, then that can equal your change of mechanical, your change of thermal energy, which goes and shows you again that the change of the energy of the system is equal to the external work. Okay. So the total of the energy of an isolated system is always conserved. And here we've got this last example here. I think this is already solving it for you as a matter of, yeah, I think it does. So the mountain climber uses a rope to drag a bag of supplies up a slope at constant speed. Show the energy transfers and transformations on an energy bar chart. Okay. And it's just showing you like you've got initial kinetic energy plus your initial potential energy is equal to your external work. And that's all going to equal out, okay, into that energy principle. And here it's just wanting to know how much work is done by the environment and the process represented by the energy bar chart. So in this case, in order for them to all equal, you've got 1 plus 2, right? Plus 1. So you have a total of 4 here. Well, you already have 4 here and you have 1 here. So what am I going to have to do? I'm going to have a -1 on here in order for that to all equal. Okay, that's the end, and I think my kids just came into the house. I'm going to stop the video and I'm going to put a reading assignment on. And so if you have any